Hello everyone, I am Assistant Professor Urmi Shah from IT/ICT Department of LJ Institute of Engineering and Technology. Today we will be starting with newer module, that is unit number 9, and it is all about spread spectrum communication. So this is the last module of our analog and digital communication subject. In this subject, we have already covered the types of communication techniques, what are the modulation schemes, the analog and digital communication techniques, how they are comparable, what are the advantages, which technique is preferred in market for specific applications. All these things we have covered in this subject, analog and digital communication. From now onwards, we will be moving ahead with the last unit of our session, analog and digital communication, which will be dealing with spread spectrum communication. This is something which is currently you all might be hearing in your news channels about the spectrum theory, which is actually applicable whenever you are dealing with any communication spectrum in industry or market level. So let's start with this unit, that is unit number 9, spread spectrum communication. In this session, I am going to cover following topics, and those topics include FHSS, DSSS, spread spectrum concept. Here we will be learning about the types of spread spectrum, which includes frequency hopping spread spectrum and direct spread spectrum, that we will be learning in this session. So let's move ahead with the topics. So firstly, what is frequency hopping spread spectrum? So as you can see over here, that signal is broadcasted over seemingly random series of frequencies. So let's take an example. If you have some specific signal that will be broadcasted for some specific range of frequency, so that is known as frequency hopping spread spectrum. Nextly, we will be discussing about what are the different types and how this spread spectrum is applicable in current market and industry. So basically, here the receiver hops between frequencies in sync with the transmitter. Eavesdroppers hear unintelligible blips. Jamming on one frequency affects only a few bits. So all this thing happens whenever we are performing frequency hopping spread spectrum. Now let's understand how this FHSS is working. So basically, this is the block diagram of transmitter circuitry of FHSS, that is frequency hopping spread spectrum. So the transmitter block covers a binary data input signal which will be given to modulator circuitry. Modulator circuitry will perform the frequency shift gain or binary phase shift gain modulation on the data which is coming as an input in form of binary. Further, the data will be processed in digital sequence form to the FH spreader. In FH spreader, the frequency hopping spreader sequence will be mixed with the sequence or the signal coming from frequency synthesizer. In frequency synthesizer, we are having input from pseudo bit noise bit source, where you will have pseudo random generator. So random sequence will be generated, and from the channel table some specific signals will be picked up by the synthesizer, and that C of T is generated by the frequency synthesizer after performing specific synthesis in related to frequency ranges of the signal, and it will be further processed to FH spreader. It is nothing but a mixer. it is going to mix up the sequence which is coming from modulator and the signal which is coming from frequency synthesizer. Now further, after performing mixing of these two signals, it will be further processed to band pass filter. All of you know that band pass filter passes a specific band of frequency and rest of the frequencies it is blocking. So that is the role of band pass filter. After band pass filter, the output will be generated will be a spread spectrum signal, that is nothing but S of t. So this way the frequency hopping process will be performed from transmitter side. Nextly, moving ahead to the receiver side. In receiver side also we will have another kind of circuitry which is having the output which is generated from transmitter side as an input in the receiver section. So basically the spread spectrum signal S of t will be the input to the FHD spreader. It is performing here demixing of signal, and again the same block diagram will be processed where pseudo noise bit source is going to generate the pseudo random sequence that will be picked up from the channel table by frequency synthesizer, and frequency synthesizer signal output will be mixed up in the FHD spreader. From FHD spreader, the output is going to band pass filter where you will have separation of two frequencies which were mixed up at the time of transmitter section, and now further the band pass filter is going to process the signals and it is going to generate the output at the demodulator section by performing demodulation technique, that is frequency shift keying and binary phase shift keying, and finally the original received signal will be in the form of binary data which was actually transmitted at the transmitter section. So this is how the whole process will be done at the frequency hopping spread spectrum. So the only difference in the transmitter and receiver block is in the transmitter at the initial stage we have modulator circuitry, while in the receiver circuit at the end we have demodulator circuit. So that is the difference between the frequency hopping spread spectrum transmitter and receiver. So now let's move ahead with the next topic in this sequence, which will be dealing with the another kind of technique which we will be using in our spread spectrum. Then how the receiver circuitry work, based on that we have an analysis that whether it is slow or fast. So basically slow and fast FHSS means the frequency is shifted by every TC second. TC means it is a communication time or channel time period. Duration of the signal element is in TS second. TS here stands for signal time duration. So always whenever you have a slow FHSS, it means that TC is greater than or equal to TS. TC is your channel time and TS is your signal time. So whenever TC is greater than or equal to TS, that means your channel is having slow FHSS, or your spread spectrum technique is having slow frequency hopping spread spectrum. And whenever TC is less than TS, you have a fast FHSS. That means whenever channel time is less than the signal time duration. Generally, why we are preferring fast FHSS? Because the fast FHSS gives improved performance in noise or another external disturbances like jamming. So this is how slow and fast FHSS are preferred. Nextly, let's talk about another features of FHSS, that is, this is the diagram of spread spectrum frequency hopping technique using MFSK. MFSK is multiple frequency shift key. Here the multiple M array FSK is having M value as 4 and K value as 2. So this is how you can see M is 4, that means you will have 4 different sequences in input 0, 0, 0, 1, 1, 0, 1. Now these are the 4 MFSK spread spectrum modules as you can see over here. Now the frequency is on the y-axis and on the x-axis you will have the input binary data. Input binary data will have some kind of pseudo random noise sequence, that is your PN sequence, and this way whenever the input data signal will be matching with your pseudo noise or random sequence, there you will have the shaded portion. So that is nothing but frequency hopping spread spectrum. Here you can see TS is your signal time duration and TC is your channel duration. Nextly, so this is an example of slow FHSS. Nextly, for fast frequency hop spread spectrum, the diagram is visible to you. You will have more number of hops compared to this one because here the TC period was greater than TS. Here you will have channel duration lesser than your signal duration, so you will have more number of matching between the pseudo noise sequence and your input binary data. So as much as more matching you will have, that much more hops you will have for your frequency spread spectrum. Again, on the y-axis you will have frequency, on the x-axis you will have input binary data and PN sequence, that is nothing but your pseudo noise sequence. And here on the x-axis in the below we will have time duration, which will be measured in terms of the symbol generated or the channel formed and the signal generated. So this is how the fast frequency hopping spread spectrum works. Now coming to the performance calculation, why we are preferring FHSS and why not another kind of frequency hopping technique? Because here large number of frequencies are used, so you will have an improved resistance to jamming. That is one of the biggest advantage of FHSS. Nextly, the another advantage we will be seeing by comparing it with the another kind of technique, that direct sequence spread spectrum. Now what is DSSS? So here in direct sequence spread spectrum, each bit is represented by multiple bits using some spreading code. The spreading code spreads signal across wider frequency band in proportion to number of bits used. 10-bit spreading code is spread 10 times bandwidth of 1-bit code. The another method which is used here is you can combine input with spreading code using XORing operation. Input bit 1 will be inverted whenever you will have it in form of spreading code bit. Then input 0 bit does not alter whenever you have a spreading code bit as 0. Data rate is equal to original spreading code and performance is also similar to FHSS. So this is all about DSSS. What is direct sequence spread spectrum? So here every bit will be represented by multiple bits. If I have a bit 1, then it will be represented by multiple bits using spreading code. So this is known as direct sequence spread spectrum. Directly I am spreading by sequence in form of multiple codes. So this is nothing but an example of direct sequence spread spectrum. You can see here the data input A is in form of single bits, Then it is again generated in form of pseudo noise bit stream, which is having multiple bits, and then at the transmitted signal the combination of A and B will be performed. That will be my transmitted spreaded code signal. At the receiver side, this received signal will be achieved, which was transmitted by the transmitter. Same way, the locally generated PN bit stream is going to be identical as B is generated above. So it is going to have a deep spreading, and then the final input sequence will be generated at the receiver section. So this is how the direct sequence spread spectrum formulation is done. Now what is the block diagram of direct sequence spread spectrum? Let's understand what are the different blocks of DSSS. So basically, the input data will be your binary data, then it will be further processed to the modulator circuitry, where we will have BPSK modulation, that is binary phase shift key. Then in the DS spreader, that is direct sequence spreader, we will have spreading of two signals, that is SD of T, that is the sequence coming from modulator, and another is your C of T, which is coming from pseudo noise bit stream. So this will be done in the DS spreader. Then the output generated will be your spread spectrum signal, that is S of T. The transmitter circuitry will have this block diagram, and the receiver circuitry will have the similar diagram with the demodulator and despreader block. So actually this is a receiver circuitry and this was a transmitter circuitry. So instead of transmitter, which is written over here, it will be a receiver circuitry. So this is one of the corrections in this slide. So the difference here in the transmitter and receiver block is, you can see in the transmitter block I have the modulator circuitry in the initial block, while in the receiver I will have demodulator circuitry at the end, which was similar in FHSS also. So basically the spread spectrum signal will go in form of S of T in DSD spreader, and in DSD spreader there will be mixing of signal in form of C of T, which is coming from pseudo noise bit source, and then it will be further processed in form of SD of T to demodulator block, and demodulator will perform demodulation of signal and will generate the binary data. So these are the two blocks, transmitter and receiver block of direct sequence spread spectrum. This is the example shown over here for direct sequence spread spectrum using binary phase shift key. So you will see over here that initially the data input signal is in form of your digital signal, and the sequence is in form of analog form. It will be multiplied and the spreading code will be generated, and further the demodulation part will be done using the same BPSK demodulator circuitry. So this is the approximate spectrum of DSSS signal. You can see over here, this is the spectrum of data signal. This is the spectrum of pseudo noise, which will be in form of channel time duration, and finally we will have it in form of spread spectrum signal. So this is the spread spectrum signal spectrum. Then we will have another kind of technique, that is CDMA, and that we will be discussing in the upcoming next session. How CDMA is different compared to DSSS, that we will be seeing in the next session. For this session, we have only studied FHSS and DSSS. So in the upcoming session, I will be discussing all this CDMA technique and another improved version of spread spectrum communication technique we will discuss in the upcoming session. For this session, following are the books which you can refer for the topics which we have covered in today's session, that is FHSS and DSSS. frequency hopping spread spectrum, and direct sequence spread spectrum. So kindly refer to this topic. In the next session, I will be discussing about code division multiple access technique, that is nothing but the CDMA technique. Thank you so much for watching this session. In the upcoming session, we will be moving ahead with this unit number 9 of your analog and digital communication subject. Thank you. Thank you for watching this session.